So, hello everybody. It's a pleasure for me to be here. And so, as Pierre said, I'm working in IO. I'm at the head of the HSQE department. So, safety is one of my major concerns today. So, in a few minutes, I'm going to try to explain to you what is our approach today to deal with that particular issue. Since yesterday and this morning, we have talked a lot about safety, which is judged by a lot of people as a crucial issue to deploy properly sustainable practices using autonomous function. So first of all, before talking about how to properly design a perception system, we need to be clear about what is the definition of autonomy. And it's one hot topic for several years. And when we talk between manufacturers, some tractor manufacturers will focus on automated function, while when we are doing robotics, in our case, robotics involve more autonomous tasks than what you can find in an scripted automated function. So there is no standard right now defining properly what are the level of automation. So we propose a pragmatism approach to be able to have the good notion and the good vocabulary, which will lead us to do better risk assessment and better categorization of what are the performances needed for our system, depending on the level of autonomy we want to achieve. So as soon as you have a function which is able to take command on the motion of the machine, so that is to say that as soon as you can have a command leading to hazards if the machine decides to go on a way where there is some bystander in the vicinity, we consider autonomous function. So at level 3, what we define as an assisted autonomy, you have the machine which is able to work alone and to decide by itself to go left or to go right, to speed up or to slow down and so on, depending on the task you want to have. So at level 3, you have a work which is done autonomously and without any perception system. In that case, all of the hazard management is done by human. So you need to have a human near the machine or on board, or maybe near the field, on another field. It's not linked to the distance between the machine and the operator, but you need to have someone who is able to detect any obstacle coming in front of or near the machine and to be able to act properly in enough time, enough speed to be sure to reach a safe state mode before the actual Earth. So that is what we call assisted autonomy. Autonomous work, but with a human supervisor around it. At level 4, you are going to introduce a perception system on your machine. So in that case, your machine is able to sense the neighborhood around it, and it is able also to send a signal to the human or to a superior system that there is an obstacle. And in that case, your system may be able to decide to stop or to reach safe state mode. So at level 4, your machine is able to detect and to take restrictive decision, to decide to go to safe state mode, for example. But you still rely on a human to make the more complex decision. And one of the most complex decisions is to decide if the obstacle is removed and if we can start again the work without causing any damage to bystander or to the crops. So at level 4, what we call supervised autonomy for us, that's directly that. You have a perception system who is able to detect, and you still rely on human to decide to start again the work. And at level 5, what we call autonomy, full autonomy for some people, machine is able to do all of these jobs alone. So autonomous work, but also to perceive if there is any obstacle in the vicinity of the machine, And there is also a supervisory system which is able to take complex decisions, especially to decide to start again when you have removed or deal with a hazardous situation. So in that case, you still have a human in the loop. That's a very important point to underline. Even if you are in full autonomy, you still have a remote operator or natural person who is aware of what is done by the machine. In that case, it can be only an alert on your smartphone or red light, green light, depending on the actual state of your machine. But you still have a human in the loop who is able to launch properly the work or to evaluate if there is any more complex event coming. For example, if you have running the morning near your field, your machine will not be able to detect that you can have some runner just in the vicinity of your field, and it could lead to additional domain hazards. So in that case, the supervisor could decide to not launch the automated work. So that is very important for us to underline the fact that even if you are in full autonomy, you still have a human responsible of doing the job safely. And you can find that approach also in other industrial sectors, like UAV, for example. You still have a pilot who is in charge to do the job properly or to supervise the job. So if you are clear about this level of autonomy, depending on your risk assessment, you are able to define the proper performances level needed for all of your critical system. For example, if you decide to target level 3, you can have, for example, some function implemented on tools in a more complex system which is not automated. So in that case, for example, an on-off valve decision, for example, it could be automated, but you do not need to perceive around the system because you still have an onboard driver, for example. So in that case, your target could be assisted autonomy. And depending on your risk assessment, you can decide just to go that way. For heavier machines, like Arduino, for example, if we left alone the machine, it's obvious that if there is a bystander, if we do not take the proper protection, we can hurt that person. So in our case, our risk assessment cross with the fact that we target to be at level 5 will lead us to normative standards which are already available, saying to us, okay, you need to have a perception system which will have a failure rate lower than 10 ppm, for example, per hour of failure. So that is very useful to have this definition to understand where you need to go to prove the performances level of your perception system or your supervisory system. And obviously, depending on the technologies needed to sense properly the environment around your robots, it will be very, very complex task to prove the performances level. When we talk about automation in the field, there is two major risks which arise. The first one is the risk to leave the field, so I'm not going to talk about that risk right now. I'm going to focus on the risk to hurt someone around the robots. There is also other risks, cybersecurity, collision with another equipment, destruction of crops, and so on. But today, we are just going to talk about the risk to hurt someone. So our approach is based on a very simple fact. When you look at the regulation, legislation, you need to, if an obstacle, a human, goes into a danger area just near the machine, you need to shut down the power. So in that case, you are going to disrupt all of the function, you are going to shut down the energy, and you need to have a guy who is going to come and to launch again the work on the field. So it's not really automated. So the approach is to have two areas around the machine. One which is immediate vicinity of the machine where you can have immediate danger. You are going to shut down your energy. And around that, a perception area where you can act and decide, and you have the time to decide either to change your trajectory, to slow down, to make an alert, to make some noise, to try to deal with the obstacle. And we consider that if you succeed to avoid that the danger is going to reach the inner area, you can decide to start again while you are still in an automated mode. And in that case, you don't need to have someone who is going to come and launch again the work. So how perceive the obstacle? It's clear that depending on the use case, it's more or less difficult. What we can say today is that there is absolutely we do not know any sensor which is able to detect human in every outdoor condition which are met by the machine in the agricultural world. So for us, that's a basic statement. We need to base our approach on a fusion of several sensors. We can use infrared thermal imager, laser, LIDAR, ultrasonic, radar, bumper, and so on. But in any case, you still need to have several technologies if you want to be able to detect with the proper performances level human in your perception area. And the main point to developing a proper perception system is first to be able to evaluate the actual environmental condition where your machine is going to act. That's very difficult because depending on the countries, depending on the crops, you can have your dino who is working to work with the sun, with the rising sun, maybe by night. So in that case, not all of the sensors are suitable for these several environmental conditions. And in any case, we need to be able to when we have defined the environmental condition, to be sure that we are going to define a proper scoring of each sensor, and to be sure that in any case which are covered by the condition of limit of condition of our machine, we are able to evaluate what will be the actual performance of this sensor and all of the integration of this sensor in our system. So it takes time, it's clear. And even if you have a proper solution, even if it's work, you still need to prove the accurate performance level. And when we talk about ppm of failure per hour, you need to have a lot of errors before being able to prove that your system is actually performing with the proper performance level. So during that time, clearly we need to rely on a human still in the loop. And that's why we consider that today it's too soon for most of the case to say that our Strader rovers are able to work alone without anybody in the field, because we do not have proven yet the proper performances level. When you look at the dyno, for example, it will be quite straightforward, because when you are working with low-lying crops, every obstacle could be considered as a human, and the robots will just have to decide, okay, there is an obstacle, I'm going to reach safe state mode, or just to ask for the supervisory what I'm going to do. As soon as you have crops which are at the same size of the human, in that case, you need to have an additional function, which is to sort between the crop and the actual obstacle. And in some case, for some obstacle, you still need to make a sort if that obstacle is a human or not. So it could be very difficult. And today, in the coming months or coming years, we are convinced that several solutions can be on the table. But as soon as you try to put artificial intelligence in your perception system, in your safety system, in that case, the time to market will be years, because you still do not know how you are going to prove that your system, based on artificial intelligence, will have the proper performances all along the operation of your machine. So today, we consider that artificial intelligence is not yet mature enough to think to introduce this feature in perception system. So just to reach conclusion, today we consider that safety indeed is a crucial issue, if we want to realize sustainable practices based on automation. So that's why we are involved in several instances. For example, we are working with RobAgri in the frame of a project which is called SolRob. We are also involved in AXEMA, the French Manufacturers Association, but also in the SEMA, where we have took the lead of a technical working group on safety of autonomous function. And the main target of that working group is just to discuss with other manufacturers, to be clear on the definitions, to be clear on the meaning of what is automation, and how we are going to propose a draft to design properly a perception system and so on. So we consider that's a global issue for every manufacturer. So if you feel concerned, please feel free to come and join us and talk with us. We will be eager to exchange with you your point of view, and if you have any advice, it would be great. Thank you.
Thank you, Cédric. You might have some questions for Cédric in regards of safety issues. Yes, there.
Hi, thank you for that interesting talk. I'm Melanie Kimmel from IAV. What is your take on these green test bodies that have been introduced to check if an artificial intelligence system is able to recognize humans?
So what is my opinion about it?
There are these, I don't know if it's German specific, but there are these kind of green test bodies that are
but it's not directly linked to artificial intelligence. It's just linked to automation. So yeah, there is a new standard which has been issued this year, saying that to prove your ability to detect someone, you need to have a small body this size. Yes, some kind of green. To be truly honest, we have decided to split into the risk assessment. First risk, are we able to detect an obstacle which is bigger than that obstacle, and are we able to detect an obstacle which is smaller than this one? Because there is still, we think, a residual risk about detection of someone who is just lying on the crop or in the furrow. So in that case, the point is that that's why we still need a human in the loop remote operator which is able to properly evaluate if we can launch the work within the proper condition. So the responsibility of the human in that case would be just to check before launching the work if there is someone lying on the crop. But yeah, it's not very. It's a good starting point.
There's another question here.
Hi. In case of level 4, actually one first question is it already used at NIO? And in this case, how you deal with problems of connectivity? Like, okay, if there's no coverage at all, or if there's connectivity loss, what happens to the robot?
Actually, we are already at level 5 for us, for example, because for the small robots, we do not need to have any critical latency supervisory or watchdog, because we are not going to harm someone with a hose. For the straddle platform, right now we are just saying that we are at level 3 for both products, and level 4 is currently under development. But the point is just we need to have watchdog to check if there is a good connectivity and to evaluate what is the speed of the robots at some time, what is the size of their perception area, and it's basic calculus of the latency. You can deal with it without any additional hazard. So you need to work on the speed of the time to break.
Okay, thank you.
There's another question. Please raise your hand again, sir. There.
Thank you for your good presentation. So, putting aside the regulations just for a little bit and asking you about technology side, how far or how close from a technology standpoint we are in order to have these autonomous robots under outdoor conditions?
As I said, it's very difficult to answer to that question with just a generic approach. If you look at the Oz, it's already at level 5. If you look at the robots for poultry, which has been shown yesterday, for example, I'm quite sure it could be reach level 5 quite easily. The only point is that when we are talking about larger rover and tractor, it's not the same. And depending on the speed, you will not have the same risk. If you are going to do an automated work at 1 mile per hour, for example, it will be much easier to deal with a level 5 than if you are going to go at 40 kilometers. So for me, the point is that today, at low speed, I'm quite convinced that we can reach with actual very basic sensors. We are able to reach level 5 without too much risk, but it will depend on your functionality, on your speed needed, and so on. So for high-speed tractor and so on, it will take some years before reaching level 5.
We have time for another question. Actually, I have one. What about regulatory framework? Do we need one, or constructors in the SEMA will be able to produce guidelines without expecting public authorities to do so?
Yesterday, there was an interesting roundtable to give some input about government expectation all around the world. And it's clear that today, from a regulatory point of view, there is still too much accident in the field. So we need to be able to design proper systems which are, we hope, able to reduce a little bit the risk. And to do that, we can first start with guidelines and standards. So manufacturers are involved to propose a proper framework just to build these standards. So first of all, we need to define what is the level of autonomy, what is the main risk linked to automation. After that, we are going to propose Type C standards able to give instruction how to design a proper perception system or to design a proper supervisory system. But OECD has explained that they want to propose some kind of machine code like what can be available for tractor. Why not? If it's suitable to be able to prove that in Europe we are doing that way, but it could also be used for China and America, yeah, why not? But the point is today we need to take the lead, because right now governments are not able to propose some regulation because they do not know exactly what we are doing. So first of all, we need to propose guidelines to explain what we are doing, how we want to do it. And after that, explaining what are the dangers, what are the hazard situations linked to automation. And after that, they will be able to regulate. So that's the goal of the Solar project, which is organized by Rob Agri today, just to make a state of the art of what is in France on the table, what are the current risks, how manufacturers deal with the actual risk, and what are the recommendations for the next step.